This is a video about one of, if not, the most important concepts in modern physics. It governs everything from quantum level particles to the future of data encryption. And to understand this concept, we need to first ask a simple question. How do you hack someone's bank information? Until the 1970s, if you wanted to exchange private information with someone, you had to use an algorithm called symmetric key algorithm to encrypt that information. Basically, you would have to meet up in person and share a secret key. Now, this common key was only known by the two of you, so only you two could encrypt and decrypt the private message. But what if you wanted to send that information without physically meeting that person? Well, you could use, for example, a phone line, but because it's not direct, it can be intercepted, so it was no longer safe. This issue led three scientists, Revest, Shamir, and Adelman, to come up with a new encryption method in 1977 that would make it essentially impossible to decrypt using modern computers. Their method is called RSA encryption and was named after their initials. So how does this RSA encryption work, and why is it nearly impossible to crack? Well, imagine that each person has an extremely large random number. This number is public, so everyone can know it. Then, you have two other really big prime numbers that are the factors of your first extremely large number. In other words, if you multiply these two prime numbers together, you will get your initial large random number. And these two prime numbers are private, so only you have access to them. So suppose, for example, your friend wanted to send you a private message. First, they would encrypt their message using your public number and send it to you. Then, in order to decrypt it, unless you know the two prime factors that make up your public number, it is pretty much impossible to decrypt the message. And I say pretty much here because even though in theory it is possible, it would just simply take a really, really long time. Even if you use the best supercomputers today, and the best factoring algorithm known as GNFS algorithm and try to find those two factors using brute force, it would still take you millions of years. But that is not the case with quantum computers. To understand why this RSA encryption method, which worked for us for almost 40 years, is at risk, we need to first understand that classical computers and quantum computers fundamentally calculate in different ways. Now, for the sake of this video, I won't dive deep into qubits or the complexity of quantum mechanics. All we need to know is, since quantum computers use qubits instead of traditional bits, the more qubits you have, the number of possible combinations of states that it can represent at a given moment grows exponentially due to superposition. And in short, superposition allows a single qubit to represent 0 and 1 simultaneously, almost in a spectrum-like manner, whereas a regular bit in a classical computer can only be either 0 or 1. To put this into perspective, with only 300 perfect qubits, you can represent more states than there are particles in the observable universe. Now let's see how quantum computers can break RSA encryption using what's called Shor's algorithm. This algorithm was developed by Peter Shor in 1994. For this explanation, we'll consider a much smaller number, say 91, and we'll call it n, and assume we don't know the two prime factors of this number. Normally, this number would be hundreds of digits long. And remember, as soon as we find these two factors, we will have access to someone else's private information. First, take a random integer a that is smaller than our number n. Let's say a equals 5. Then, raise 5 to powers of 1, 2, 3, and so on, and write down the results. Then we divide each of those results by our initial big number, 91. Here, we're interested in the remainders because if you notice, at some point, the remainders will start to cycle periodically. And we'll call this period R. In our example, r equals 6. Once we find r, Shor's algorithm tells us that we can find the two prime factors of our large number n by using the equation here. In this equation, the GCD here stands for greatest common divisor. And if we finally substitute our values, we get 13 and 7. With an extremely large integer n, a quantum computer with a sufficient number of qubits can leverage superposition to simultaneously process all possible combinations of the powers of A and their remainders when divided by n. This is what allows quantum computers to efficiently find the period r as well. Now, this is a great oversimplification, but the main reason why classical computers are not fit for these tasks has to do with their inherent sequential and linear nature. They rely on iterative methods to calculate these powers and try to find the period r one by one. So when n is really big, the period r can also be astronomically large, making the process impractical. Not to mention, Shor's algorithm is designed specifically to exploit the quantum nature of qubits, so it only makes sense to use quantum computers for such tasks. So what does all this mean? Well, in order to keep our data safe from the day quantum computers become accessible and affordable, scientists are now trying to come up with new ways of encryption that would keep our data safe even from quantum computers. But at the same time, quantum computers are being developed and improved upon so quickly that soon we can expect to see the birth of the quantum internet. And this internet will take advantage of superposition and properties of entanglement that it would allow us for secure communication, an extremely precise GPS system, an extremely precise measurement of time, and so on and so forth. And the possibilities are endless. Before I end the video, I want to talk a little bit about a common misconception that a lot of people have about quantum computers. So when people hear the term quantum computers, they assume that they're going to replace all our current computers completely. But that's not quite right. You see, quantum computers, they excel at very specific complex problems that traditional computers struggle with, like optimization and processing large amounts of data. But for everyday tasks like running a calculator app or browsing the internet or just running simple algebra, our current computers are more than capable at it. So in the future, we can expect to use both of these computers at the same time.